Okay, so this is still on the Unit 6 exam review, and I am going to go through the improper integral problems. Okay, so taking a look at this first integral, you know that it's improper because one of your bounds is negative infinity. So there's a couple things that can make an integral improper. One of them is having one of the bounds be infinity or negative infinity, and the other is that if the function is undefined over the given interval. So in this case, we see that infinity, so we know that it's improper. And so the way that we handle this is we're not allowed to kind of plug in the infinity, but we can take the limit as a approaches this negative infinity, and then we're going to evaluate the integral from a to 1. All right, so then we rewrite it. And what we have left in the denominator here, again, if this is going to be a u substitution to integrate this, the reason that I know it's a u sub is because this kind of looks like a chain rule if I was going to take the derivative. So if it kind of looks like chain rule, u substitution might be a good strategy. So I'm going to let u be that denominator part, not to the power. And so we know the derivative of u, again, with respect to x, right, is just going to be 2, multiply both sides by that dx, so you get 2 dx. That's not an exact match to what's left. I need to get rid of this 2, right, because it's just a 1 in the numerator. So I'm going to say 1/2 du equals dx. And whenever you have a definite integral with u substitution, you need to adjust your bounds. So I'm going to say that my new limits, right, I'm going to say that a, the original bound was at a, and now when I plug a in for the x, I get 2a minus 3. The other bound was at 1, so when I plug 1 into u, I get 2 minus 3, which is a negative 1. Okay? So now I'm going to rewrite, so we're going to say this is equivalent. That limit just drops down. I didn't actually take the limit yet, so you just rewrite it. So I still have the limit as a is approaching negative infinity, but now it's going to be 1/2 the integral from 2a minus 3 to negative 1, and now I'm integrating 1 over u squared du. So again, if this is a du, that means the variable here has to be a u, and that these bounds of integration are now u values. Well, the good news is that I know how to integrate this, so I'm going to think of this as u to the negative 2 power instead. Okay, so if I think of that as u to the negative 2 power, okay, I'm just going to recopy the limit, because you kind of, way back from chapter 1, you still kind of write that word limit until you actually evaluate the limit. So I rewrite that, and I'm going to leave this 1/2 out there. So when I integrate this, again, I'm thinking of it as u to the negative 2 power, so I'm going to add 1 to it, which makes it a negative 1, divided by that number, and we're going from 2a minus 3 to negative 1. All right, and I'm just going to take a moment to kind of rewrite that and kind of clean it up. Again, this limit just keeps coming down. I didn't do anything. That's like the last thing that I'm going to deal with. Okay, so all right, a negative 1 means it's in the incorrect part of the fraction. So if I move this into the denominator, it'll be u to the first power, and I'm going to pop the negative from here. I'll just float that into the numerator. So this is equivalent to negative 1 over u. Okay, and I just did that little simplification step to make it easier for me to plug in. And I guess I'm running out of space. I guess I'll have to go over here. So this is equivalent. Again, that limit just gets recopied this whole time while I'm dealing with this integral here. All right, so fundamental theorem of calculus means I plug in the top number. So when I plug in that top number, I get negative 1 over negative 1, which is 1, minus, because that's what the fundamental theorem says to do. Then I plug this in for u. So it's a negative 1 over 2a minus 3. All right. So now what am I doing? Well, you could rewrite this so that it's a plus there, okay? But now I'm ready to actually plug in, okay, infinity. We're kind of evaluating this limit as we're approaching infinity, negative infinity here. So if you plug in a really, really, really huge negative number, okay, this denominator is going to be very, very big and negative. So essentially this piece right here approaches 0 because it's a, it's a positive, right? Because minus negative, right? But it's going to get really huge, so it'll be 1 over some huge negative number, and that's going to go to 0. So essentially, I guess I'll just write it under here. Essentially, this is the, I took the limit, sorry. So it's just going to be 1/2, okay? 1 minus this piece goes to 0 as you take the limit as you approach negative infinity. So you have 1 minus 0, which is 1, times 1/2, which is 1/2. Notice here that I got a number as an answer. If you get a number, right, so if you don't get infinity or negative infinity, right, if you get a number, we say that that converges. So essentially, the area under that curve, the sum of that's going to converges to 1/2, okay? So there's an example of an improper integral. This is an integration by parts here, so I wanted to stick to the improper integrals on this video, so I'm going to go ahead to page 4. Alright, so on page 4, again, part D was an integration by parts, so I'm focusing on the improper integral, so I'm going to look at E. Again, we know that this is improper because I see an infinity right as one of the bounds, so those are the most obvious improper integrals. And so I'm going to say that this is equivalent to the limit as a approaches infinity of the integral from 0 to a of e to the negative x dx. Okay, then from there, I'm going to integrate this, okay? So, again, the limit just comes down because I'm not actually taking the limit. It's kind of at the end. But I can integrate e to the negative x. If you need to do a u substitution, you can, okay? But hopefully now you can kind of see that's just going to be negative e to the negative x. If you're not sure, think about this. Take the derivative. Recopy this times the derivative of the exponent. That'd take you back to a positive there. And we're going to evaluate that from, from 0 to a. Okay, sorry, that's a 0. And now I'm ready to apply my fundamental theorem of calculus, and then I'll evaluate the limit. So my fundamental theorem says first I plug in a, so I get negative e to the negative a minus what you get when you plug in 0. So it's going to be a minus a negative e, right? So that turns to a positive e to the negative 0 is just 0. Okay, so just watch your negatives there. And now I'm ready to actually take the limit. So you may want to rewrite this negative exponent. It might be easier for you to understand. So I'm going to take a minute, an extra line of work. I know you're sick of writing that limit a million times. But I'm going to say that negative e to the negative a is the same thing as negative 1 over e to the a. And then anything to the 0 is 1. So I'm just going to put that in there. Okay, now I'll take my limit. I just took that moment because it's easier for me to see when I plug this infinity, and again, I'm plugging the infinity in there, okay, that this piece here is going to go to 0. So if you can see that way back in that step, that's fine, but I just chose to do it here. So this is going to be 0 plus 1, which is 1, so we say that this converges to 1. And again, that converges business is going to play a part next unit, or 2 units from now, okay? All right, and then we'll kind of move on to F. In F, you'll notice that it doesn't have an infinity in the bounds, but if you plugged in one of the bounds here, if you have a 0 in the denominator, that is bad news. So this is still, by definition, an improper integral. So we are going to take the limit as a approaches 0, because that's kind of the trouble spot, the problem point, I think I called it in the notes. And we're going to go from negative 1 to a, right? Because we're not really allowed to plug in 0. So we're going to get really, really close to it. That's what, that limit is allowing us to do. And I'm going to go ahead and call that x to the negative 2 dx. All right, so from there, go ahead and integrate that. So I'll just go down here. So we're going to say that's equivalent to the limit, again, is that a approaches 0. And I'm going to go ahead and integrate this. So all you're going to do is add 1 to the exponent, divide by that number, and then we want to apply our fundamental theorem there. So we get to here. And then, let's see, we're still going to take the limit as a is approaching 0. Oops, how did I scoot up? I would probably take a minute and rewrite this. I would rewrite it as -1 over x, and then apply my fundamental theorem so that I don't get tangled up in the algebra. So we'll say that's equivalent to the limit. Right now in this step I'm going to apply the fundamental theorem, so that limit just gets recopied. So first I plug in a, so I get -1 over a minus what you get when you plug in the denominator, or when you plug in 1 there. So that's -1 over 1. Okay, so now when you kind of clean that up, if I plug in a 0 here, okay, if you plug in 0 there, that thing blows up. So essentially what you're doing is you have to say, well, this piece here, that part's easy, right? You're going to get a +1 on this piece. But what happens here? That thing's going to be taking off. It's going to be negative, and if you're dividing by something really, really small, that thing's headed to -infinity there, okay? So because -infinity plus 1 is still -infinity, we say this one diverges. So the difference between this example and the previous is up here, our answer was a number. But here, okay, our answer was negative infinity, but if you get infinity or negative infinity, that diverges. Okay, in G, we'll notice that the problem for this function is at x equals 0. Now, since 0 isn't one of the bounds, I kind of called that a problem point kind of within. So this is where you need to actually break the integral up. So remember, our properties of integrals say that we're allowed to say this is the same as the integral from -2 to 0, then I'm going to pop that up and call it x to the -4th dx, plus the integral from 0 to 3. Okay, so my integral properties allow me to rewrite it like this. And again, I picked 0 because that's what would make the denominator 0 there. So now I'm going to have to break this up into 2 separate limit problems, right? So I'm going to have the limit, so we'll say this is going to be the limit as, we'll call it a approaches 0, and we'll go from -2 to a of x to the -4th dx. And then plus, I'm going to just assign a different letter, so I'm going to say different variable this, so I'll take the limit as b approaches 0, integral from b to 3. So this almost becomes kind of 2 mini problems. Okay, lucky for me, this is not very difficult to integrate. So again, we just bring that limit down until you actually evaluate it. So I'm just integrating here. So you add 1 to the exponent, divide by that number, and we have to evaluate that from -2 to a. And then plus, I'm just going to get this one. The limit is b approaches 0, and add 1 to the exponent, divide by that number, so we get here. We're going to evaluate that from b to 3. All right, so now it is your fundamental theorem. You may want to take an extra line to kind of rewrite this so that when you plug in. So I would probably rewrite this as -1 over 3x cubed. That'll make it a little easier for you to plug in. Okay, so I'm going to take that extra minute and kind of simplify it algebraically so that I don't make a mistake. Alright, so once you have that, now you can go ahead and apply your fundamental theorem. I think I can fit it, so let's see. I still have my limits. Again, I didn't evaluate the limit yet, so that just comes down. And now my fundamental theorem says first I plug in a minus what you get when you plug in -2 there. So be careful here. So when you plug in a -2, -2 cubed is -8. Then that times 3 gives you a -24. Okay, and then, but it's a negative up there, so a negative and a negative, right? So just kind of watch yourself on your negatives there. Okay, so that's 1/24. Okay, then plus, now you have to do the same thing on this side. I didn't evaluate the limit yet, so just go ahead and bring that down. So you plug in 3. 3 cubed is 27. 27 times 3 is 81, so you get negative 1 over 81. And then when you plug in a b, it's minus what you get when you plug in b, but that's minus a negative, so that'll be a plus 1 over 3b cubed. Alright, now you're ready to actually evaluate your limits. So if you, quote-unquote, plug in, right, a 0 here, you're really taking the limit as a gets really, really close to 0. So if you plug in 0.0000001 or something, okay, it's 1 divided by something really, really tiny. This is going to approach infinity. So we've got, plug that in, you're going to get like a negative infinity and then minus a 24th, okay? So you have a negative infinity, and then plug in over here, and you're going to get negative 1 over 81 plus infinity there, okay? And so those infinities do not cancel. This whole thing is going to diverge, because as soon as you see an infinity, right, you don't know which infinity is more powerful, but this thing is diverging. Okay, so this piece goes to negative infinity, because of that negative 1 up there, and then you've got minus 1/24th, again that's not really going to matter, and then minus 1 over 81 plus infinity, these infinities, so therefore diverges. Alright. Okay, so in this one, this is an improper integral because 0, this bound here, if you plug in 0, it makes the denominator 0. So I kind of say there's like a problem point at x equals 0. And so what I'm going to do is I'm going to rewrite this integral from 0 to 4. And I'm just going to pop that up into the numerator and say it's this. That's the equivalent. And that there's a problem there. So I'm going to rewrite that as the limit. Okay. So we're going to take the limit as a approaches 0. And then we will integrate from a to 4. Of x to the negative 1/2 dx. And so to integrate this, you're going to add 1 to the exponent, divide by that number. So we're still going to be taking the limit as a approaches 0. So when you add 1 to the exponent, it becomes positive 1/2. Dividing by 1/2 is the same as multiplying by 2. And we've already integrated, so now our bounds, we're just going to evaluate it from a to 4. Okay, so I'll come down here and apply my fundamental theorem of calculus. Again, that limit keeps following me down until you actually take the limit. So from here, we've got 2 square root 4, remember, to the 1/2 power is the same as a square root, minus what you get when you plug in a, so it would be minus 2 square root a. Okay, and now I can actually evaluate the limit. We know that this piece here, square root of 4, is going to be 2, times 2 is going to give me a 4. So I get 4 minus, when I plug in 0, the square root of 0 is 0. So 0 times 2 is 0, so you get 4 minus 0, which is 4. This is a number, so if you get a number there, we say that it converges to that number. So in this one, that converges. Okay. So I think on this review, that takes care of all the improper integrals.